Good day, I'm Dr. T and welcome to my office. So today I want to talk about the water cycle. This was originally going to be 2 videos, but after my gases and meteorology video going over an hour, I figure I better break this into 2 videos. And so this kind of, I think, leads on most nicely from the meteorology because we were talking a lot about precipitation and rain and the like, and well, that's part of the water cycle. So let's talk about water cycle, but first I want to mention just briefly cycles in general. Earth is out in space, we're floating, it's pretty much a closed system. You know, a little bit of material comes from space and lands on Earth, a little bit of material leaves Earth and goes out into space. In absolute terms, for a human, it's a lot of material. We're talking tons, but on a global scale, it's a very tiny amount. So effectively, we're a closed system. As such, if I've got some water, it's just going to get recycled. It doesn't get made and destroyed, it gets recycled. You don't dispose of it, you recycle it. And nature is going to do that, and that is going to be our water cycle. We're going to see the same thing for rocks, we're going to see the same thing for different elements. We're going to get these cycles going on. And the water cycle is kind of the most in-your-face cycle, the one you can really see happening. So I want to talk about the water cycle. Now, last time when I did weather, I just kind of started off with, hey, there's water in the air. But I kind of want to talk a little bit about how the water got there. So if we do a water cycle, and here's a classic image of a water cycle. You know, it's kind of looping, so we can start anywhere. But we've got some water, and the water could be in the ocean, it could be on land in the form of lakes and rivers, or moisture in the soil, being sucked up by trees, etc. And that water is going to start evaporating. You can evaporate water off the ocean. This is one of the reasons why the United States gets a lot of our moisture from the Gulf of Mexico, is it's evaporating water from the ocean and blowing the breeze in. This is also why, say, the Pacific Northwest is a temperate rainforest. It's getting lots of water off the ocean, and then it's running into the mountains and it's dumping the water on the windward side. But you're also getting water off the land. And so you're evaporating water off the land. You've got moist soil, the water's going to evaporate. Transpiration, this is plants sucking up water from their roots, using it to transport materials that they need, and then they're dumping it out their leaf as a gas. This is going to dramatically increase the amount of water that is leaving your land. It can actually change the local climate quite profoundly. You can actually get a very small water cycle within your local area. The Smoky Mountains aren't smoky, they're foggy, and they're foggy because of the transpiration. They're just pouring so much water into the atmosphere, and it's got to go somewhere. And so you get these foggy, cloudy environments that kind of looks like it's covered in smoke. Absolutely gorgeous. So we've got this water coming up. It could be from the form of plants or whatnot. And now it's going to go up into the atmosphere and it's going to precipitate down. Now, depends on where it precipitates, because it can pull up from one way, blow over someplace else, and dump someplace else. So just because it sucked up from where you're at doesn't mean it's going to come down there. Which is why some regions are particularly dry. Any water you got hanging out there, that's going to be sucked up and whisked away, and you're not going to get any fresh water. Think the Atahara Desert in Chile. The rains don't come. The water is evaporated, but the water doesn't come back. They're in an incredible rain shadow of the Andes Mountains. So you've got your water moving over. It's going to relocate. Now, if you're evaporating from the ocean and raining into the ocean, okay, we got a very up and down cycle. Nice little circle, all good. But if instead we're going to evaporate from land or evaporate from ocean and blow over land, and it's going to start pouring down on the land, that gets a little bit more interesting. So we're going to pour down the land. It's going to start running, and you got the classic streams to brooks to small rivers to big rivers, and then eventually it runs out typically to the ocean. Not always. It can go into a hydrologic basin. I have only read this word. I am butchering the pronunciation. I'll put the word up on the screen. But hydrologic basins are basically where the water all flows to one spot, but it doesn't flow into the ocean. The Great Salt Lake or the Dead Sea would be examples of these. But you get the idea. The water, gets bigger and bigger. It goes into rivers and flows out to the oceans. Now, sometimes it's going to pause along the way, depending on the topology. It may run into an area where it kind of gathers into a lake, where the lake still flows out. It still leaves. The water leaves the lake, but it kind of pools up before it does so. Classic. We can see the Great Lakes like this. You got a lot of the water that's hitting Michigan, lower parts of Canada are going to flow into the Great Lakes, and eventually they're going to head up the St. Lawrence Seaway and flow into the ocean. But it takes a while. You got some big lakes up there, and it's going to flow out. But you got a lot of water. Obviously, biological systems can affect this as well. Beavers are particularly famous for making lakes, or, well, beaver ponds, as the case may be. And so they can slow down the water. And this can profoundly impact the local ecosystem. You can imagine just fast-flowing river, maybe even an intermittent one that doesn't flow throughout the year if you're in a fairly dry environment. This particular picture is from Idaho. And so you've got dry environment, but this lush green strip where if the beavers weren't there, that river just kind of zoom on through, but the beavers make dams, it slows the water down. It doesn't stop the water. It slows the water. The water still goes through, but it provides moisture and an ecosystem and profoundly changes ecosystems. Beavers are one of the more profoundly impactful species on the planet, and they can just create ecosystems from their munching. It's kind of cool to make a bunch of dams. Okay, so you got this idea. You can flow through. You might slow down, go through a wetland, maybe a marsh or a bog, etc., where the water and land are kind of 50-50. That's not the definition. It's an area where you're partially covered by water, or completely covered by water, at least part of the time. So you can have your wetland, the water's moving slowly. Obviously, it could still be evaporating. Or it may be the water's not slowing down, it's going straight into the ocean in a nice quick river. So it does depend on what you're doing. But you get the idea. Evaporation or transpiration gets the water up in the atmosphere. Meteorology happens, it precipitates, and then it flows back along the land. Now, I want to get into one quick idea how we can go a little bit more detailed into this somewhat simplistic view of our water cycle, and that is the idea of a drainage basin. I've already been alluding to drainage basins, but this is the area where, just due to the shape of the terrain, the topology, water is going to be funneled down towards a direction. This is one where you can kind of zoom in, zoom out, as you would like to do so. But if I've got, say, an area of land, any droplet of water within a drainage basin, if it precipitates on there, it's going to flow down into wherever that drainage basin goes. So if it's all going into a river, it's all going to go into that river. If that river then meets up with a tributary, then you get the idea. Here's an example of the drainage basin for the Mississippi River, which flows out into the Gulf of Mexico. You have a massive area. So water that falls in Montana, Illinois, Ohio, Oklahoma, Tennessee, they're all going to find their way to the Mississippi River. And so you get this idea of funneling it in. But, if you look at the map, you've got water that's falling in Indiana. It's going to go to the Mississippi River, but the next state north, Michigan, it falls in Michigan, and the way the land is shaped, it doesn't go towards the Mississippi River. It doesn't go south. It's generally going to go north-ish into the Great Lakes. And so the Great Lakes are their own drainage basin. The other map I have here is kind of a global view of this. And so we're looking at a little bit zoomed out, so not necessarily which river goes where, but where it ends up, which ocean or which gulf, etc. Which I got to say, it's the ocean. We subdivide it for clarity, but they're all connected. It's one big ocean. But we're going for which part of the ocean you're going into. And so if you kind of look at this one, obviously if you're in the Mississippi River drainage basin, then you're going down to the Gulf of Mexico via New Orleans. But if you're, say, in Georgia, you're not going to go through the Mississippi River. If you're on the western side of Georgia, you're still going to go through various rivers into the Gulf of Mexico. But if you're on the eastern side of Georgia, you're going to probably go through, say, the Savannah River or other rivers on the eastern side, and you're going to go straight out into the Atlantic. This map also has colored in gray various endromic basins, remember, those are the areas where the water goes to, but it doesn't go to the ocean. It will eventually evaporate. Great Salt Lake or Dead Sea, those would be examples. There are quite a few of those. So we've got this idea of drainage basins. And, well, you'll notice that where the water ends up always tends to be a bit on the salty side. The ocean is famously salty. The Great Salt Lake is the Great Salt Lake. The Dead Sea is legendarily just insanely salty. And there are other locations. And generally, wherever the water ends, it's going to be salty. And the question, of course, is why? Well, the answer ends up coming around to being the water is bringing with it stuff. Now, one of the concerns of a drainage basin that if you spill some kind of pollutant, it's going to be travel through the drainage basin and get out the other end. So if I make a spill of some kind of toxic chemical in Ohio, it's going to go through the Mississippi River and out into the Gulf of Mexico. The pollution down there definitely means ecosystems have a lot of challenges, especially kind of near where the Mississippi River drains out, just because we're collecting pollution from such a large area. But pollution isn't the only thing we're collecting. As the water is going across the land, it's interacting with the rocks and soils, and it's going to be dissolving water-soluble chemicals in there, like salt. Or I should say salts. Sodium chloride is by far the most popular, but there's quite a few other things, magnesium chloride, quite a few other salts. And so these are going to flow with the water. Now, once they get to their final destination, the ocean or the Great Salt Lake or whatnot, they're going to evaporate off. The water comes in, the salts come in, the water leaves by evaporation, but the salts don't leave. And so they're going to start building up more and more and more salts. And hey, the ocean is salty. This is why. We've extracted the salt from the land and we've transferred it into the ocean. Now, as we're flowing through the land, I've actually described it a little bit overly simplistic. So let's look at the ratio of water we have on our planet. And so most of the water on the planet is going to be oceans. We're talking 96.5% of the water on the planet is in our ocean. For freshwater, basically the ones that don't have too awful much salt in, and in theory you could purify and drink pretty easily. You can still do ocean water. You can do desalination. It's an absolute pain. There's a reason we don't do it very often. It's expensive and hard to do, but it can be done. But for our fresh water, only about 2.5% of our global supply of water would be fresh water. Now, for an absolutely essential resource, that's not a lot, but it gets worse. Of that fresh water, the vast majority of it is ice. 68.7% is going to be ice in the polar ice caps or glaciers. Now, this data is a few years old. I think it's from like 1993. So these numbers are probably a smidge less. These will almost certainly have changed. But you get the general idea. It's going to have the same flavor. About 2.5% of our water is fresh water. Of that, only about 1.2% is on land, per se. And of that, only about 22% is in a river or a lake. So we are talking a tiny percent of a tiny percent of a tiny percent. But I have been omitting something, and that is there's actually a fairly decent percentage of our fresh water. It is flowing. It's not trapped as ice. It's just not on the land. It's under the land. We've got groundwater. We need to talk about groundwater because that actually ends up becoming an incredibly big deal, both from a societal point of view, but also, if you notice this, that's where most of our fresh flowing water is, or fresh liquid water is going to be, is in the form of groundwater. Now, in order to talk about groundwater, I need to talk a little bit about the ground itself. Generally speaking, we casually say, oh, I got the tree planted in the dirt outside, or, I dug in the dirt for the garden. And this, in colloquial English, yeah, that's fine. I totally do that. But technically speaking, dirt has been separated from the ground. So if I dig up some material from the ground and I put it in a bag, I got a bag of dirt. But while it's still on the ground, while it's still connected to the material, we call that soil. And so we've got the soil. Now, soil is not all the same, as almost certainly you have noticed. And there's a couple of ways of classifying it. And there's kind of 4 major components that I want to look at. And they're all relatively the same idea. Well, one of them is very much different, but the 3 I want to look at are very similar concepts. They're clay, silt, and sand. These are going to be inorganic components, so not carbon bearing. Basically, they're ground up rocks. They're what happens after you get weathering of your rocks, and they turn into small particles. Clay are going to be the smallest particles, very, very tiny particles. They pack in really, really tight. As such, they don't have much in the way of voids, and water's not really going to be able to permeate them very well. It won't be flowing through, it won't be seeping in. It's mostly just going to kind of try and stay on top of your clays, especially if you have a lot of them. The next size up, kind of the medium size, they're still quite small particles, is going to be the silts. Water is going to be able to soak into those pretty good. It's not really going to flow through them as well, but water is going to soak in nicely. As you get larger, we get into sand. Now we got much larger voids, and the water is going to be able to start flowing through the sand. Depending on what you want to do with your soil, you're going to want different blends of clay, silt, and sand to change the physical properties of your soil, including water permeability, but there is more going on for that. Now, I'd be amiss to not mention we've got humus. Humus is going to be the organic components, basically the dead and decaying plant matter, animal matter per se, the carbon components of our soil. That's what gives the, that nice black rich soil, it's black rich soil. So if you think of the classic, really good farmland, it's that dark rich soil. And that's going to be the organic components, the humus. And that's going to have a lot of the micro and even macronutrients that the plants need in it. But those are also going to be interacting with the inorganic components of the soil. If you're wanting your optimal soil for what you're working with, you're going to want to balance your inorganic components as well as the size of the inorganic components. So you've got a lot going on with your soil. The reason I want to mention this is this idea of permeability. So depending on how well the water can flow through the soil, that does affect what's going to happen below the ground. If you've got a lot of clay, the water's going to hit the soil and just keep running. Same goes for things like asphalt. Several years ago, there was a hurricane in Houston, Texas. Houston had lots and lots of asphalt, not a lot of nice soil to soak up the water. So they got a lot of water and a lot of flooding because the water couldn't soak into the ground. But if you have soil instead of asphalt, and that soil hopefully has got a bit of sand going on, it's going to be able to suck up the water and drain it away in the form of groundwater. And this leads to the idea of aquifers and the water table. So if I've got a stream flowing through, the water is flowing through the stream, but it's also going into the soil around it, and it's going to be flowing around in the soil. Now, obviously, we've got soil. We also could have gravel and rocks and other larger materials. Rocks are going to have a similar narrative. If you've got a bunch of small rocks, you're going to have some nice voids to flow through. Good old gravel. If it's going to be solid stone, some of those have lots of little cracks where the water can flow. Some of them don't. The water doesn't flow through that. And so it is going to depend on what your particular materials are going on. But if the water can flow through the surface, through the soil or the gravel or whatnot, you're going to get, as the water travels through the stream, it's going to leach out into the ground, and you're going to have water in the ground pretty much at the same level as the stream. And we're creating an unconfined aquifer. We call an aquifer, a stream underwater is an aquifer. The height that this gets up to is called the water table. And this is the classic idea of a well. If you dig a hole near a stream or a river, or even fairly far away from it, and you dig it down deep enough till you get to the water table where that water is flowing, then the water will pool in the bottom of the well. Now, this is great if you want a well. This is not so great if it's your basement. And so now you're going to have a sump pump to suck the water out and to shove it outside the house. Otherwise, your basement constantly likes to flood. This will, of course, vary depending on the topology. So if you've got some high areas, it's going to kind of flow down. And as the water is flowing, you can accidentally build your house in the middle of an underground river. This is a classic problem when you're having to waterproof your house, put in, say, drains, which are generally just giving the water alternate channels to flow. The classic French drain is basically a ditch filled in with gravel, and the water can flow through the gravel and get around your house. Maybe put in a nice pipe that it can flow into even easier. So you can have these underground rivers in the form of aquifers. But that's an unconfined aquifer. By that definition, it sounds like there might be such a thing as a confined aquifer, and there very much is. So a confined aquifer, you're going to have a layer of impermeable material, soil or rock, and then a layer of permeable material, soil, rock, gravel, whatever, then another layer of impermeable material. So you have this sandwich, and so the water, if there's an opening at the top, say up on a mountain, the water, as it precipitates on the mountain, it flows into the ground, going into this contained aquifer, and it's going to be in there. Now it's actually going to be under pressure, because it's going to be under pressure because it's packed up. It's in a pipe, effectively. The two impermeable layers of soil or stone are going to be creating effectively a pipe in the middle, and it's got this giant tower of water on one end pushing down, and so it's going to be under pressure. So if you dig a well into there and you crack into it, it's going to start spurting up because it's under pressure. And this is called an artesianal well. Different locations may or may not have them. It entirely depends on your geography. Generally speaking, you're going to be down the little ways from a mountain if you're going to have artesianal wells. So you need this confined aquifer as well as the ability to get it charged up on the mountain. So it has to be confined and fairly high up. Now, one of the areas when it comes to aquifers that we do need to mention very briefly is that the recharge region, where the water is falling and soaking into the soil, that recharging process, one, can introduce pollutants. If you've got wells that allow chemicals into an aquifer, or that pollution happens on that recharge area, or if it's an unconfined aquifer just generally on the ground, the pollution is not just going to go down the river, it's going to go down in through the aquifer. Aquifers are underground rivers. The other thing, though, is because we're slowly soaking through soil, aquifers are massive underground rivers, but they generally flow very slow. And you can have massive underground lakes as well. Same kind of idea. You got a bunch of water trapped in the soil and stone layers. But the recharge rate may be very slow. The water very slowly trickles in. So if you've got wells, great, you're pumping out water, but you can very easily pump out far more water, far faster than it's going back in. So your water cycle can get a little bit wonky because you're pulling out water faster from your aquifer than it's going in. It's not like a normal surface river where if you pump up the water, it's replaced, it's flowing through. Whereas on the underground, you can pump it down and it takes a lot longer to refill. Although I should point out, the Colorado River doesn't reach the ocean. We pump out all that water and it eventually dries up in Mexico. It never makes it to the ocean anymore because we use up all the water from the Colorado River. So you can suck out a surface river just as easily as an aquifer, but the aquifer, you don't usually see it. Now, as you remove the water, the land may shuffle and you may get sinkholes, etc. But you get the general idea. You have a renewable resource over very long time scales, so that some of your aquifers you need to consider to be non-renewable because the time scales that they take to replenish are going to be well more than human lifetimes are going to be, and effectively are non-renewable resources because it's just so slow to renew them. Okay, so I think I've hit most of the major points I wanted to on the water cycle. I want to draw your attention to groundwater. It's a massive and important topic. Practical engineering. I know I usually do the further reading on the front part of the video, but I'm going to do this towards the end. Practical engineering does a lot of really interesting demos and explanations of groundwater and water systems, and looking at the physics and engineering side of it. So I will link to his channel in the description. Encourage you to check it out if you're interested in covering a little bit more of this. Otherwise, I will see you in future videos. The next one up, I'm going to be hitting rocks and the rock cycle.